Let's study the paper that put a number on the heart of a dark matter halo. It's Schive, Liao, Wu, Wang, Chui, Broadhurst and Huang, 2014, published in Physical Review Letters, Volume 113, Article 261302. The title is Understanding the Core Halo Relation of Quantum Wave Dark Matter, PSI-DM, from 3D Simulations. George, I want to do this one all the way down to the mathematics, spoken out loud, because our listener is literally building a fuzzy dark matter simulation to reproduce this exact result.
I love that framing, Alice, because this paper is one of those rare cases where a single clean scaling law falls out of a very deep symmetry, and then a giant supercomputer simulation goes and confirms it. And the punchline is a relation you can write on the back of a napkin. The core mass is proportional to the halo mass to the 1/3 power, m sub c proportional to m sub h to the 1/3. Everything else in the paper is the story of why that exponent is 1/3 and not 1/2 or 1 or 2/3.
Let's make sure everyone is standing on the same ground first. Fuzzy dark matter. What is the physical picture before any equations?
So the standard cold dark matter picture treats dark matter as classical particles, little billiard balls that only feel gravity. Fuzzy dark matter, which this paper calls Psi-DM. Wave dark matter says the dark matter is an extraordinarily light boson. The mass they quote is around 10 to the minus 22 electron volts. To give you a sense of scale, an electron is about 500,000 electron volts, so 10 to the minus 22 electron volts is roughly 28 orders of magnitude lighter than an electron. It is absurdly light.
And when something is that light, its quantum wavelength becomes astronomical. Literally.
Literally astronomical. The de Broglie wavelength for a particle that light, moving at galactic velocities of tens or hundreds of kilometers per second, comes out to something on the order of a kiloparsec, which is thousands of light years. So the wave nature of the particle is not some microscopic footnote. It is smeared out across the entire core of a dwarf galaxy. The whole galaxy core behaves like one gigantic quantum wave.
Which is why they can describe the entire dark matter halo with a single wave function.
Exactly. The dark matter is non-thermally produced. It is a single coherent scalar field, and you describe it with one complex wave function psi that stretches across the galaxy. And that is the crucial move. Instead of tracking 10 to the 90 particles, you evolve one field. And the equation that field obeys is the Schrödinger-Poisson equation, which is going to be our workhorse for the whole conversation.
Before we write it down, why does anyone want dark matter to be this weird? Cold dark matter works beautifully on large scales.
It does on large scales, it is a triumph. The trouble is all on small scales, galaxy scale and below. There are two famous headaches. One is the missing satellites problem. Cold dark matter predicts a steeply rising number of small halos, so the Milky Way should be swarming with thousands of little dwarf galaxies, and we see far fewer. The other is the cusp core problem. Cold dark matter simulations produce halos with a density that spikes upward toward the center, a cusp, and follows what's called a Navarro-Frenk-White profile. But when astronomers actually measure dwarf spheroidal galaxies, the dark matter looks like it has a big flat core in the middle, not a spike.
And fuzzy dark matter fixes both at once through the uncertainty principle.
Right. And that is the elegance of it. You cannot squeeze a wave into an arbitrarily small box. The uncertainty principle resists compression. So there's an effective quantum pressure. The paper calls it a quantum mechanical stress tensor that holds structure up below a certain scale, the gene scale. Below that scale, structure is suppressed. That simultaneously wipes out the smallest halos, fixing missing satellites, and flattens the central cusp into a core, fixing cusp core. One knob, the boson mass, and two problems dissolve.
And there's a bonus the paper mentions. This mass scale isn't arbitrary. It can come from a non-QCD axion.
Yes, they cite Chiu's axion model. So the 10 to the minus 22 electron volt scale isn't just tuned by hand to fit galaxies, it can emerge naturally from particle physics, from string-inspired axion-like fields. That's part of why the community got excited. Now there's also a competitor worth naming, warm dark matter. It also suppresses small-scale structure, but through free streaming rather than a wave.
And warm dark matter has the catch-22 problem.
The catch-22, which I always enjoy. To make a core big enough, about a kiloparsec, in warm dark matter, you need the particle so light and so warm that it would have prevented the dwarf galaxies from forming in the first place. You can't have the core and the galaxy. Fuzzy dark matter escapes this. The earlier Schive, Broadhurst Nature Physics paper, reference 39 here, showed PSI-DM clears the catch-22. This letter is the sequel that quantifies the internal structure.
Okay, let's write the Schrödinger-Poisson equation, George, spoken out loud, in the co-moving coordinates the paper uses.
Here we go. Equation 1, open bracket, I times the partial derivative with respect to tau, plus 1/2 times the Laplacian, minus a times v, close bracket, acting on psi, equals 0. Let me say that again slowly because every term matters. You have I, the imaginary unit, multiplying the partial derivative of psi with respect to tau, the time variable, then plus 1/2 del squared psi, where del squared is the Laplacian, the sum of second spatial derivatives, then minus a times v times psi, where a is the cosmic scale factor and v is the gravitational potential. All of that equals 0.
So it is exactly the Schrödinger equation you'd see in a quantum mechanics class. I partial psi partial t equals minus 1/2 del squared psi plus v psi, just rearranged and living in an expanding universe.
Precisely. The 1/2 del squared is the kinetic term, it's the wave spreading. The a times v term is the potential energy, gravity. And the scale factor a out front on the potential is the only overt sign that we're in cosmology, in an expanding box. Now the second equation, Poisson's equation, closes the loop. Equation 2, del squared v equals 4 pi times, open parenthesis, the modulus of psi squared minus 1, close parenthesis.
Let's unpack that. Del squared v equals 4 pi times bracket mod psi squared minus 1.
The modulus of psi squared, that's ESI times its complex conjugate, is the mass density of the dark matter. So the local density of dark matter sources the gravitational potential, which is just Newtonian gravity written as a field equation. The minus 1 is the average background density subtracted off, because in an expanding universe, only the overdensity relative to the mean drives gravitational collapse. Where mod psi squared is bigger than 1, you're denser than average, gravity pulls in. Where it's less than 1, you're underdense.
So it's a closed, self-consistent loop. The wave function tells the potential how to curve. The potential tells the wave function how to move. Schrödinger feeds, Poisson feeds Schrödinger.
That's the whole game, and it's beautifully non-linear because of that feedback. Now I have to say a word about the units, because these are what the paper calls normalized or code units, and they hide some physics that we'll want to resurrect later. The co-moving length x is normalized by a specific combination. Open parenthesis, 3/8 pi, times h naught squared, times omega m naught, close parenthesis, to the minus 1/4 power, all times m psi over h bar to the minus 1/2 power.
Slow that down. The length unit is built from 3/8 pi h naught squared omega m naught to the minus 1/4 times the boson mass over h bar to the minus 1/2.
Right. H naught is today's Hubble parameter, omega m naught is the matter density fraction of the universe, m psi is the boson mass, and h bar is the reduced Planck constant. The key thing to notice, and hold on to it, is that the boson mass appears in the length unit. So the physical size of everything ends up depending on the boson mass. Time is normalized similarly, and psi itself is normalized by the square root of rho m naught over m psi, where rho m naught is the present background mass density. The upshot, in these units the equations are clean and parameter-free, but the boson mass is baked into the conversion back to kiloparsecs and solar masses.
And this is exactly the equation our listener's simulation is integrating. Gamer solves this on an adaptive mesh, and the Jaxian differentiable solver solves basically this same Schrödinger-Poisson system. So when we talk about scaling symmetry next, we're talking about a symmetry their code literally inherits.
That's the perfect setup, because the entire paper hangs on one property of equation 1 and 2, the scaling symmetry. This is the mathematical heart. Let me state it carefully. When the density is high, mod psi squared much greater than 1, so we can ignore that background minus 1. And when the scale factor A is approximately constant over the short time a core forms, the Schrödinger-Poisson system is invariant under a one-parameter family of transformations.
One parameter, call it lambda.
Call it lambda, any positive real number. The transformation is tau, the time, goes to lambda to the minus 2 times tau. The space coordinate x goes to lambda to the minus 1 times x. The wave function psi goes to lambda squared times psi, and the potential v goes to lambda squared times v. Let me repeat that quartet because it's the DNA of the paper. Time scales as lambda to the minus 2. Length scales as lambda to the minus 1. Psi scales as lambda squared. Potential scales as lambda squared.
So if I take any solution of the equation and rescale it by these powers of lambda, I get another perfectly valid solution.
Another exact solution. There is not one soliton, there is an infinite continuous family of solitons, all self-similar, all related by this stretching. A big fat low-density soliton and a tiny dense soliton are the same solution viewed through different values of lambda. That's why the paper keeps saying self-similar solitonic cores. They're all the same shape, just scaled.
Let me try to see why those particular powers work. Take the kinetic term, 1/2 del squared psi. Space scales as lambda to the minus 1, so each spatial derivative brings a factor of lambda. Two derivatives, that's lambda squared, and psi itself scales as lambda squared, so del squared psi picks up lambda squared from the derivatives times lambda squared from psi, giving lambda to the fourth.
Good. Now the time term I partial psi partial tau. Tau scales as lambda to the minus 2, so the time derivative brings a factor of lambda squared times psi, which is lambda squared. So that's also lambda to the fourth. Kinetic and time terms both scale as lambda to the fourth, they balance. And the potential term of v psi is v, which is lambda squared times psi, which is lambda squared, again lambda to the fourth. Every single term in equation 1 scales the same way, as lambda to the fourth, so it factors out, and the equation is unchanged. That's the symmetry.
And Poisson checks out too. Del squared v is lambda squared from the derivatives times lambda squared from v, lambda to the fourth. And the source, mod psi squared, is lambda squared times lambda squared, lambda to the fourth, both sides lambda to the fourth. Consistent.
Both sides scale identically, so Poisson is invariant too. Beautiful. Now here's where it becomes physics. The paper then asks, how do the observable physical quantities of a core scale under lambda? The core radius, the core density, the core mass, and the core energy. And this is equation. Well, it's the line right after the transformation. The quartet becomes x sub c goes to lambda to the minus 1, x sub c, rho sub c goes to lambda to the fourth rho sub c, m sub c goes to lambda times m sub c, and e sub c goes to lambda cubed e sub c.
Let me say those four out loud because our listener will want to memorize them. Core radius x sub c scales as lambda to the minus 1. Core density RHO sub c scales as lambda to the fourth. Core mass m sub c scales as lambda to the first power. Core energy E sub c scales as lambda cubed.
And every one of those follows from the transformation we just wrote, plus dimensional bookkeeping. The radius is a length, so it goes as lambda to the minus 1, same as x. The density is mod psi squared, and psi goes as lambda squared, so density goes as lambda to the fourth. Straightforward.
The mass is trickier. Walk me through why core mass scales as lambda to the first power.
Mass is density integrated over volume. Density scales as lambda to the fourth. Volume is length cubed, and length scales as lambda to the minus 1, so volume scales as lambda to the minus 3. Multiply them, lambda to the fourth times lambda to the minus 3 equals lambda to the first power. So core mass scales as lambda. That's the single most important scaling in the paper. So let me say it once more. Mass equals density times volume. Lambda to the fourth times lambda to the minus 3 gives lambda to the 1.
And now I can immediately see a gorgeous consequence. Core mass scales as lambda, core radius scales as lambda to the -1. So if I multiply core mass by core radius, the lambdas cancel. Lambda times lambda to the -1 is lambda to the 0, which is 1.
You just derived the core mass-radius relation, and it's the cleanest fingerprint of a soliton. The product of core radius and core mass is a constant independent of lambda. Say it in words. The core radius times the core mass is a fixed number, which means the core radius is inversely proportional to the core mass. A more massive core is a smaller core, R sub c, proportional to 1 over m sub c.
That is deeply counterintuitive if you think classically. Pile on more mass, the thing gets smaller.
It's the signature of self-gravitating quantum objects, and it's the same math as a white dwarf or a neutron star, believe it or not. More mass means stronger gravity, means it compresses. The quantum pressure fights back, but scales differently, and equilibrium lands you at a smaller radius for larger mass. In the fuzzy dark matter soliton, add mass and it shrinks. This is why a tiny dense soliton and a big fluffy one are two ends of the same lambda family.
Let's nail the last one, the energy. Core energy scales as lambda cubed. Why?
Energy in this system, think of the kinetic piece, is basically the integral of the gradient of E psi squared over volume, up to factors. Gradient of p psi brings one spatial derivative, a factor of lambda, acting on p psi, which is lambda squared. So gradient of psi is lambda cubed. Squared, that's lambda to the 6th. Integrate over volume, lambda to the -3. Lambda to the 6th times lambda to the -3 is lambda cubed. So energy scales as lambda cubed. And we'll use that in a moment for the deepest result in the paper.
Before we get there, let's ground it. This abstract lambda family, does nature pick a particular lambda? Or do all sizes of soliton actually occur?
Great question, and it's the philosophical hinge of the whole letter. The scaling symmetry says all solitons are allowed. It does not by itself tell you which one sits inside a given halo. So there's a missing piece of physics. What selects lambda? And the answer, which they establish through simulation, is that the halo you live in selects your lambda through energy balance. Hold that thought, it's the climax.
Let's now write down the actual soliton density profile, because our listener needs the functional form to fit their simulation output. This is equation 3.
Equation 3, the soliton profile. Rho sub c of x equals a numerator over a denominator. The numerator is 1.9 times a to the -1 times open parenthesis m psi over 10 to the -23 electron volts close parenthesis to the -2 times open parenthesis x sub c over kiloparsec close parenthesis to the -4. The denominator is open bracket 1 plus 9.1 times 10 to the -2 times open parenthesis x over x sub c close parenthesis squared close bracket all raised to the 8th power. And the whole thing has units of solar masses per cubic parsec.
Let me read that denominator back because it's the famous part. 1 plus 0.091 times the ratio x over x sub c squared, and that whole bracket is raised to the 8th power.
The 8th power. That's the shape everyone quotes, so you have a chord profile. Near the center, when x is much smaller than x sub c, the bracket is approximately 1, and the density is flat, it's a constant core. That's exactly the flat core that fixes the cusp core problem. As x grows past x sub c, the bracket grows and that 8th power makes the density fall off steeply. It's an incredibly convenient closed form, and the paper says it's accurate to 2% out to about 3 core radii, x less than roughly 3x sub c.
And they define x sub c very specifically.
Very specifically, and this matters for anyone fitting data. X sub c is the radius at which the density drops to 1/2 of its central peak value, the half-density radius. You can actually check the number, set the profile equal to 1/2 of the peak. The peak is at x equals 0, where the bracket is 1. Half the peak means the denominator must equal 2. So 1 plus 0.091 times, open parenthesis, x over x sub c, squared, close parenthesis, all to the eighth equals 2.
So the bracket itself has to equal 2 to the 1/8 power.
2 to the 1/8, which is about 1.09. So 0.091 times the ratio squared equals about 0.09. The ratio x over x sub c is about 1. It's self-consistent by construction that 0.091 is tuned so that x sub c is exactly the half-density radius. Nice internal check for your listeners fitting code. If you fit that profile and your half-density radius doesn't match your x sub c parameter, you've got a bug.
And then core mass, m sub c, is the mass enclosed within x sub c.
Within x sub c, yes, that's their definition of core mass, the mass inside the half-density radius. And they give you two more useful facts. The mass enclosed within 3x sub c is about 95% of the total soliton mass, so 3 core radii is essentially the whole soliton. And the half-mass radius, the radius containing half the total mass, is about 1.45 times x sub c. So there's a small dictionary. X sub c is the half-density radius, 1.45 x sub c is the half-mass radius, 3x sub c is basically the edge.
Now let's read the boson mass dependence of equation 3, because you flagged the mass hides in the units.
Look at the profile. The density is proportional to, open parenthesis, m(p)(i) over 10 to the minus 23 electron volts, close parenthesis, to the minus 2. So core density scales as the boson mass to the minus 2 power. A heavier boson gives a less dense core at fixed core radius in kiloparsecs. And separately, we'll see the physical core radius scales as the boson mass to the minus 1. Everything you predict, core sizes, minimum halo masses, depends on this one unknown particle mass, which is exactly why the community wants to measure it, and exactly why your listener's simulation is trying to pin down the relation independently.
There's a subtlety in that profile I want to flag, the a to the minus 1 out front, and the fact that the profile is redshift dependent. Let's do the cosmological redshift scaling now, because it's a second, separate scaling on top of the lambda symmetry.
Yes, and people conflate these two scalings all the time, so let's keep them cleanly separate. The lambda scaling we did is at fixed scale factor, fixed cosmic time. It relates different solitons to each other. The redshift scaling is different. It's how a single soliton's description changes as the universe expands, as it grows. The paper introduces a second set of rescaled variables to absorb the redshift dependence.
These are the primed variables.
The primed variables. They define tau prime, x prime, psi prime, v prime as follows. Tau prime equals a to the 1/2 times tau. X prime equals a to the 1/4 times x. Psi prime equals psi, unchanged. And v prime equals a to the 1/2 times v. With those rescalings, the Schrödinger-Poisson equation takes a redshift-independent form, meaning a drops out. So the primed frame is the frame where cosmic expansion has been scaled away, and the physics looks static.
And the consequence they draw is about the co-moving soliton radius.
The consequence is, at a fixed peak core density, the soliton radius in comoving, unprimed coordinates scales as a to the minus 1/4. As the universe expands, a grows, and the comoving core radius shrinks as a to the minus 1/4. That's a slow evolution, but it's real. And it's why in their figure 1, the solitons at different redshifts, z equals 12, 8, 2.2, 0.9, and 0, all lie on the master soliton curve only after you apply the proper lambda and a rescalings. Raw, they're offset. Rescaled, they collapse onto one line.
That figure 1 is the money plot for validating a code. 5 halos at 5 different redshifts, plus a convergence test.
The convergence test is important for your listener specifically. They take the z equals 0 most massive halo and rerun it at 8 times higher resolution, the filled circles in figure 1, and the core profile is unchanged. That's how you prove the core is physical and not a resolution artifact. Anyone reproducing this must do the same. Refine the mesh, confirm the core radius and peak density don't move. If your core shrinks every time you refine, you haven't resolved it, you're looking at grid noise.
And they overlay a soliton from the merger experiments and a cold dark matter halo fit by an NFW profile for contrast.
Right, the filled squares are AZ equals 8 halo from a cold dark matter simulation, fit by Navarro-Frenk-White, the dot-dashed cuspy line. It has no core, it just keeps rising toward the center. The fuzzy dark matter halos, by contrast, all show that distinct flat solitonic core sitting on top of an NFW-like outer envelope. So the picture that emerges, and this is the paper's central structural claim, is soliton core in the middle, NFW halo outside, and they always coexist.
Let's state that structural picture clearly, because it's the thing the title calls the core halo configuration.
Every virialized fuzzy dark matter halo has two parts. In the center, a gravitationally self-bound solitonic core, the ground state standing wave, smooth and chord. Surrounding it, an extended halo that looks like classical cold dark matter, an NFW profile, but it's not smooth. It's full of fluctuating density granules, lumps created by the quantum wave interference of many excited modes sloshing around.
And the size of those granules is the same as the size of the core. That's not a coincidence, it's a clue.
It's the central clue, and I want to make sure we come back to it, because it's how the uncertainty principle sneaks from the core out into the whole halo. The granule size equals the core diameter because both are set by the local de Broglie wavelength, which is set by the velocity dispersion. Hold that, it's going to be the physical mechanism behind the core-halo relation.
Okay, let's build up to the main result. First, let's just state the empirical relation they find, equation 4, and then derive it.
Equation 4, the empirical core-halo mass relation. M sub c is proportional to a to the minus 1/2 times m sub h to the 1/3 power. Say it plainly, the core mass is proportional to the scale factor to the minus 1/2 times the halo mass to the 1/3 power. Two pieces, a redshift piece, a to the minus 1/2, and the halo mass piece, m sub h to the 1/3.
The 1/3 is the star of the show. Let's define halo mass first so it's unambiguous.
The halo virial mass m sub h is defined as 4 pi over 3 times x sub vir cubed times zeta of z times ρm naught, where x sub vir is the co-moving virial radius, ρm naught is the present background density, and zeta of z is the overdensity at virialization, a factor from spherical collapse theory. Zeta of z is about 350 at redshift 0 and about 180 at redshifts above 1, roughly 18 pi squared. And critically, they emphasize this is the same virial mass definition used for cold dark matter. No special pleading.
Why is that same definition point important?
Because they argue the outer halo doesn't know its quantum. Once an object exceeds the gene's mass on its way to collapsing, the dynamics is essentially cold collapse. There's an iconal approximation, where wave mechanics reduces to particle mechanics in the short wavelength limit, and it holds all the way until virialization. So the halo forms exactly like a cold dark matter halo. The quantum weirdness is confined to the very center, the core. That's why they can bolt a soliton onto a standard halo. They're not fighting the large-scale structure formation, just adding a quantum heart.
And figure 2 shows equation 4 holding over 3 orders of magnitude in halo mass.
From about 10 to the 8th solar masses to 5 times 10 to the 11th solar masses. Different symbols for halos at different redshifts, from the 2 megaparsec and 40 megaparsec cosmological boxes, plus open symbols from a 20 megaparsec box, plus crosses tracing the evolution of a single halo through time. And the scatter around the relation is less than a factor of 2 everywhere. That's remarkable for such a simple power law across 3 decades in mass.
Now, the derivation. This is the part our listener really wants. Why 1/3? Take us through it, George, and let's not skip a step.
Going to do it in 3 moves. Move 1. The scaling symmetry gives us a relation between core mass and core energy. Move 2. The simulations show the relevant energy is the halo's energy, giving core mass in terms of halo velocity dispersion, and that's the uncertainty principle acting non-locally. Move 3. Apply the virial theorem and the definition of virial mass, and out pops m sub h to the 1/3. Ready?
Ready. Move 1.
Move 1. Pure scaling. We established that under lambda, core mass scales as lambda and core energy scales as lambda cubed. So core energy is proportional to core mass cubed. E sub c proportional to m sub c cubed. Now flip it around to get core mass in terms of energy. Take the cube root, m sub c is proportional to E sub c to the 1/3. But watch, I want it in terms of specific energy, energy per unit mass, because that's what connects to the halo.
Specific energy, that's E over m.
E sub c over m sub c. Core energy scales as lambda cubed, core mass scales as lambda, so the specific energy E sub c over m sub c scales as lambda cubed over lambda, which is lambda squared. Meanwhile, core mass itself scales as lambda to the 1. So core mass scales as lambda, and specific energy scales as lambda squared, which means specific energy scales as core mass squared. Therefore, core mass is proportional to the square root of the specific energy. M sub c proportional to, open parenthesis, E over m, close parenthesis, to the 1/2.
That's equation 5, essentially.
That is exactly equation 5, made rigorous by the merger experiments. Let me read equation 5 in the primed variables. M sub c prime equals alpha times, open parenthesis, the modulus of E prime over m prime, close parenthesis, to the 1/2 power. Where alpha is a dimensionless constant close to 1, E prime is the total energy of the system, and m prime is the total mass. The modulus, the absolute value, because for a bound system, the energy is negative and we want the magnitude.
And they establish equation 5 not from cosmology, but from controlled soliton collision experiments. Tell me about those, because it's a beautiful piece of numerical physics.
This is my favorite part of the paper, honestly. They wanted to isolate what determines the core scale, stripped of all the messiness of cosmological structure formation. So they set up controlled experiments. Take a box, no expansion. A is constant, 0 background density. Drop in multiple solitons at random positions with 0 initial velocity. Let gravity pull them together. They collide, they merge, the system sloshes and violently relaxes and eventually settles into a virialized equilibrium.
How many runs, and how did they vary them?
29 runs total. They varied the total mass m and the total energy E. And crucially, for the same m and E, they repeated with different realizations. Different numbers of initial solitons, anywhere from 4 to 128 solitons. Different soliton sizes, different starting positions. The whole point was to test whether the final relaxed state remembers its initial conditions or not.
Because if the final core scale depends only on the conserved quantities, total mass and total energy, and not on the messy details of how you started, that's a profound statement.
That's the statement, and it's the intuition behind equation 5. A relaxed virialized system should lose memory of its initial configuration. It should depend only on the globally conserved quantities, total mass m and total energy E, assuming no net angular momentum. And that's what they find. Figure 4 plots core mass against the square root of specific energy, and all 29 runs, regardless of how many solitons or what sizes, fall on one line with slope-matching equation 5. The constant alpha comes out close to 1.
And they're careful about conservation.
Very careful. This is good numerical hygiene. They use adaptive mesh refinement, so every soliton is resolved by at least 10,000 cells, and they verify that total mass m and total energy E are conserved to within a few percent through the whole violent merger. If your energy isn't conserved, your specific energy is garbage, and equation 5 is meaningless, so they earned the right to plot it.
Now, the definitions of those primed energies spoken out, because our listener will compute exactly these.
In the primed redshift-independent coordinates, the kinetic energy E sub k prime equals 1/2 times the integral of the modulus of the gradient of psi prime squared over d cubed x prime, so 1/2 integral grad psi prime mod squared. The potential energy E sub p prime equals 1/2 times the integral of mod psi prime squared times v prime over d cubed x prime. And the total mass m prime equals the integral of mod psi prime squared over d cubed x prime, which is just the total dark matter mass. Standard quantum mechanical expectation values, kinetic energy from the gradient, potential energy from density times potential.
Now, the physical interpretation of equation 5, which is the deepest sentence in the paper. Give it to me.
Here it is. The right-hand side, the square root of specific energy, The square root of the modulus of E over m, that is a velocity. Energy per unit mass has units of velocity squared, so its square root is a velocity. And specifically, it's the halo velocity dispersion, sigma sub h, the typical speed at which stuff is moving in the halo. So equation 5 says core mass is proportional to the halo velocity dispersion, m sub c proportional to sigma sub h.
And on the left-hand side, we bring back the scaling.
On the left, the lambda scaling told us core mass is proportional to lambda, and core radius is proportional to lambda to the -1. So core mass is proportional to 1 over core radius. M sub c proportional to 1 over x sub c. So substitute that into equation 5. 1 over x sub c is proportional to sigma sub h. Rearrange, x sub c times sigma sub h is a constant of order 1.
The core radius times the halo velocity dispersion is a constant of order 1. That is the uncertainty principle.
That is the uncertainty principle. Position times momentum of order h bar, written for an entire galaxy. In their units, x sub ca prime times sigma sub h prime is approximately 1. Position uncertainty, the core size, times momentum per unit mass. The velocity dispersion is of order 1, which in the units where h bar over m is 1, is exactly the uncertainty relation. The size of the quantum core is set by how fast the halo is moving. Faster halo, bigger momentum, smaller allowed position spread, smaller core.
And the word they stress is non-local. Why is that the surprising part?
Because the uncertainty principle, as you learn it, is a local statement about one particle, its own position spread times its own momentum spread. But here it relates a local property, the core size in the very center, to a global property, the velocity dispersion of the entire surrounding halo. The core knows how fast the outer halo is moving and sizes itself accordingly. That's non-local, and it's not obvious it should hold. The soliton is in the middle, the halo velocity dispersion is a property of material at all radii, yet they're locked together.
And the physical mechanism for that non-locality is the granules. Bring it home.
This is the beautiful closure. Remember, the halo is full of fluctuating density granules, and their size equals the core size. Why? Because a granule is an interference blob, and its size is the local de Broglie wavelength, which is h bar over m times v, inversely proportional to the local velocity dispersion. So the granule size is set by sigma sub h, and the granules are physically the same scale as the core. So the halo velocity dispersion through the granule size directly imprints the core size. The granules are the messengers that carry the halo's velocity dispersion into the center and tell the soliton how big to be. It's a kind of quantum thermalization, and they note a follow-up paper, Wong and collaborators, will do the eigenmode decomposition to explain the detailed physics.
I love that. The granules aren't noise, they're the coupling. Okay, move 3. We have core mass proportional to root-specific energy. Now bring in cosmology, the virial theorem, and get the 1/3.
Move 3. In the cosmological halos, they verify that equation 5 holds if you take E prime and M prime to be the halo's own energy, E sub H prime, and the halo virial mass, M sub H prime. So core mass equals alpha times the square root of the modulus of halo energy over halo mass. Now apply the virial theorem. For a self-gravitating system in equilibrium, the total energy magnitude equals half the potential energy magnitude. The modulus of E sub H prime equals the modulus of E sub P prime over 2.
And they use the spherical collapse estimate for the potential energy.
They use the standard result that the potential energy of a roughly uniform sphere is about 3/5 gm squared over r. And in their units it becomes the modulus of E sub H prime is approximately 3 times m prime sub h squared over 10 times x sub vir prime. So 3m sub h prime squared over 10x sub vir prime. That's just gravitational binding energy of the halo, self-gravity of a sphere of mass m sub h and radius x sub vir.
So now plug that into equation 5.
Plug in. Core mass equals alpha times the square root of the halo energy magnitude over the halo mass, which is 3m sub h prime squared over 10x sub vir prime, all divided by m sub h prime. The m sub h prime squared over m sub h prime leaves 1 power of m sub h prime, So inside the square root, we have 3m sub h prime over 10x sub e via prime. Core mass equals alpha times the square root of 3m sub h over 10x sub via. And restoring the redshift factor gives an a to the minus 1/2 out front. So m sub c equals alpha times, open parenthesis, 3m sub h over 10x sub via, close parenthesis to the 1/2, times a to the minus 1/2.
We're almost there. Core mass goes as the square root of halo mass over virial radius. Now we need to eliminate the virial radius using the definition of virial mass.
Exactly, and this is the last substitution. The virial mass definition says m sub h equals 4 pi over 3x sub via cubed zeta rho m naught. Solve that for x sub via. The virial radius is proportional to the cube root of the halo mass. X sub via proportional to m sub h to the 1/3. Bigger halo, bigger radius, and it grows as the 1/3 power because mass is radius cubed times a density.
So now substitute x sub via proportional to m sub h to the 1/3 into core mass equals root of m sub h over x sub vi.
Substitute. Core mass proportional to the square root of m sub h divided by m sub h to the 1/3. M sub h over m sub h to the 1/3 is m sub h to the 1 minus 1/3, which is m sub h to the 2/3. So core mass proportional to the square root of m sub h to the 2/3. And the square root of m sub h to the 2/3 is m sub h to the 1/3.
There it is, core mass proportional to halo mass to the 1/3.
There it is. M sub c proportional to m sub h to the 1/3. The 1/3 exponent is the composition of two things. A square root from the energy mass scaling, that's the 1/2, acting on a 2/3 power that came from the virial radius, eating 1 power of mass out of the ratio. 1/2 times 2/3 is 1/3. That's the whole story of the exponent. And with the a to the minus 1/2 we carried along, you recover equation 4 exactly. Core mass proportional to a to the minus 1/2 m sub h to the 1/3.
Let me make sure I can retrace it in one breath, because this is the thing to remember. Energy scales as mass cubed from the symmetry, so mass goes as root of specific energy. Specific energy is velocity dispersion squared, so mass goes as velocity dispersion. Velocity dispersion from the virial theorem is root of halo mass over virial radius. Virial radius is halo mass to the 1/3. So mass goes as root of halo mass over halo mass to the 1/3, which is root of halo mass to the 2/3, which is halo mass to the 1/3.
Flawless. And notice what each ingredient contributed. The Schrödinger-Poisson scaling symmetry gave the energy-mass relation. The uncertainty principle, non-locally, gave the connection to velocity dispersion. And ordinary gravitational virial equilibrium of the outer halo gave the mass-radius relation. 3 different pieces of physics, and they conspire to make 1/3. That's why the paper is satisfying. It's not a fit, it's a derivation.
Now the full formula with all the redshift and cosmology factors, equation 6, because that's what you actually compare data against.
Equation 6. The complete core-halo mass relation. Core mass equals 1/4 times a to the minus 1/2 times, open parenthesis, zeta of z over zeta of 0, close parenthesis to the 1/6, times, open parenthesis, m sub h over m sub min naught, close parenthesis to the 1/3, all times m sub min naught. Let me pass the pieces. The 1/4 and the m sub min naught set the normalization. The a to the minus 1/2 is the redshift scaling. The ratio zeta of z over zeta of 0 to the 1/6 is a slowly varying correction from the overdensity factor evolving with redshift. And m sub h over m sub m in naught to the 1/3 is our 1/3 power law.
And m sub min naught is a fundamental mass scale built from constants. Spell it out, because the boson mass lives here.
Sub min naught equals 375 to the minus 1/4 times 32 times pi times zeta of 0 to the 1/4 times rho m naught times, open parenthesis, h naught times m psi over h bar, close parenthesis to the minus 3/2 times omega m naught to the minus 3/4. It's a mouthful, but the important dependence is buried in that h naught m psi over h bar to the minus 3 halves. Numerically, it evaluates to about 4.4 times 10 to the 7th times em sub 22 to the minus 3 halves solar masses, where m sub 22 is the boson mass in units of 10 to the minus 22 electron volts.
So m sub min naught scales as the boson mass to the minus 3 halves.
The boson mass to the minus 3 halves, heavier boson, smaller minimum mass scale, and this m sub min naught is close to the minimum halo mass that can exist in fuzzy dark matter, the smallest thing that can hold a core, about 4.4 times 10 to the 7th solar masses over m22 to the 3 halves. That's a real falsifiable prediction. Cold dark matter has no such flaw, it makes halos all the way down. Fuzzy dark matter says there's a smallest galaxy, and its mass is set by the boson mass.
And figure 2 shows equation 6, the dashed line, running right through the simulated halos.
With alpha set to 1 and typical cosmological parameters, the dashed analytical line from equation 6 threads the data across all 3 decades of mass. They note the low redshift massive halos in the small 2 megaparsec box scatter a bit more, probably a finite box effect, too small a volume to sample big halos properly. But the massive halos in the larger 20 megaparsec box converge nicely onto the prediction. In all cases, the deviation of core mass from the relation is less than a factor of 2.
This is exactly the number our listeners' project is chasing. Let me say it plainly for them. The entire FDM simulation effort in 49-FDM_quantum_simulation is trying to independently measure this m sub c versus m sub h relation, the slope, from their own gamer adaptive mesh runs and their Jaxion differentiable solver.
And it's worth being honest about how hard that is, because it reframes why the paper is a landmark. To measure the slope, you need to resolve the core, tens of parsecs, inside a halo that lives in a box of megaparsecs. That's a dynamic range of tens of thousands, which is why Schive needed adaptive mesh refinement and GPU acceleration in the first place. Their spatial resolution was down to 60 parsecs in a 2 megaparsec box. Your listener is fighting the same battle: refine hard enough to trust the core, big enough box to get a fair sample of halo masses. The tension between those two is the whole engineering problem.
And that's exactly why the project has both an adaptive mesh approach and a differentiable one. The differentiable solver lets you actually fit the slope as a parameter, propagate gradients, and ask what boson mass is consistent with a measured slope.
Right, and here the physics we derived is a gift, because it tells you the answer should be robustly 1/3 if the code is correct, independent of the initial power spectrum. The paper stresses this: the core halo relation relies on the virialization of each individual halo, not on the large-scale initial conditions. That's why a tiny 2 megaparsec box gives the same slope as a 20 megaparsec box. So if your listener's simulation gives a slope that drifts far from 1/3, that's a signal something's off, either unresolved cores or a bug in the gravity solver, not new physics. It's a fantastic validation target precisely because the theory pins it down so tightly.
Although, and I think this is important for them, the normalization, the constant outfront, and the exact redshift dependence are where the real science is, because those carry the boson mass.
That's the subtle point. The slope, 1/3, is almost guaranteed by the symmetry plus virial equilibrium. It's a consistency check. The interesting mass-carrying quantities are the normalization of the relation and the core radii themselves. Those depend on m-psi, so measuring the slope validates your code, but measuring the normalization and comparing it to observed dwarf galaxy cores is how you'd actually constrain or rule out the boson mass. That's the deeper prize.
Let's go through the physical core radius formula, equation 7, since it's the observational handle.
Equation 7. The physical core radius, r sub c, which is a times x sub c, the scale factor times the comoving radius. R sub c equals 1.6 times m22 to the minus 1 times a to the 1/2 times, open parenthesis, zeta of z over zeta of 0, close parenthesis to the minus 1/6 times, open parenthesis, m sub h over 10 to the 9th solar masses, close parenthesis to the -1/3 in kiloparsecs.
Read me the two dependencies that matter most.
Two things. First, R sub c is proportional to the halo mass to the -1/3 power. -1/3, so more massive halos have smaller cores. This is the halo scale echo of the soliton mass-radius relation we derived: bigger mass, smaller size. Second, R sub c is proportional to M22 to the -1, the boson mass to the -1. Heavier boson, smaller core. So if you see a dwarf galaxy with a 1 kiloparsec core, that directly constrains the boson mass. The whole observational program of fuzzy dark matter flows from this equation.
And it inverts the intuition beautifully. In cold dark matter, big galaxy, big everything. Here, big halo, smaller quantum core.
Because the quantum core is a balance between gravity and quantum pressure, and gravity wins harder in a bigger, hotter halo, compressing the core. It's genuinely non-classical intuition, and it's testable. Now let's cash out the predictions the paper makes, because they're bold and specific.
Prediction 1, the dwarf galaxies, solving the small-scale problems.
For present-day dwarf satellite galaxies, plug in their halo masses, and equation 7 gives kiloparsec-sized cores. That's exactly the size of the flat dark matter cores observed in dwarf spheroidals, like Fornax. And equation 6 with the minimum mass logic gives a minimum halo mass around 10 to the 8th solar masses. So fuzzy dark matter predicts there simply are no dark matter halos below roughly 10 to the 8th solar masses. That's how it solves the missing satellites problem. The small ones can't form, and the kiloparsec cores solve the cusp core problem. Both small-scale controversies from one boson mass.
They derive that minimum halo mass carefully. Walk me through it, because it uses the core being the whole halo idea.
The smallest possible halo is one where the soliton core essentially is the halo. There's barely any surrounding envelope. Now, their definition of core mass, mass within R sub c, the half-density radius, is about 25% of the total soliton mass. So for the smallest halo, they set core mass equal to 1/4 of the halo mass. M sub c equals M sub h over 4. Plug that into equation 6 and solve, and you get a minimum halo mass, M sub min of z, equal to a to the -3/4 times zeta of z over zeta of 0 to the 1/4 times M sub min 0. At redshift 8 for M22 equals 0.8. That's about 3 times 10 to the 8th solar masses.
Consistent with the independent theoretical prediction they cite.
Consistent with Bozek and collaborators' prediction, and consistent with Figure 2, where the smallest halos are indeed soliton-dominated. It all hangs together. And note the boson mass they use, 0.8 times 10 to the -22 electron volts, comes from the earlier Nature Physics papers fit to the Fornax dwarf's stellar phase space distribution. So it's an independently measured mass, not a free parameter here.
Prediction 2, the high redshift bombshell. Massive galaxies at redshift 8 with dense cores.
This is the speculative, exciting end of the paper. Take a present-day galaxy with a typical halo mass of 2 times 10 to the 12 solar masses, a Milky Way-ish halo. Equation 6 gives it a core mass around 5 times 10 to the 8th solar masses, with a core radius around 160 parsecs today. Now ask about a galaxy with the same halo mass but forming at high redshift at ZD equals 8.
And the redshift factors kick in hard.
They kick in through the a to the -1/2 in core mass and the a to the 1/2 in radius. At high redshift, a is small, so a to the -1/2 is large. The core mass is enhanced by a factor a to the -1/2, and the gravitational acceleration near the core, which is core mass over core radius squared, is enhanced by a to the -3/2. So a high redshift galaxy of the same halo mass has a much more massive and much more compact core. For 2 times 10 to the 12 solar masses forming at Z equals 8, they get a core mass around 2 times 10 to the 9 solar masses inside just 60 parsecs.
And that has consequences for how the first quasars and black holes formed.
That's the conjecture they end on. Such a dense, compact core provides a deep gravitational well that can funnel gas rapidly into a tiny central region. If the baryon fraction there matches the cosmic mean, That core captures at least 4 times 10 to the 8th solar masses of gas, and they note the 60 parsec core radius is only about twice the 30 parsec thermal gene's length of gas, near the Lyman alpha cooling temperature, around 10 electron volts, so the gas is right on the edge of collapsing. That could seed prompt formation of early stellar spheroids and supermassive black holes, potentially explaining quasars seen as early as redshift 7, which are otherwise very hard to form fast enough in standard pictures.
So the same one-third relation that fixes tiny dwarf galaxies also, at the other extreme of redshift, might explain the earliest monster black holes. That's a huge dynamic range for one scaling law.
It is, and it's why the paper landed in Physical Review letters. One clean relation, derived from a symmetry, verified in simulations, reaching from the smallest galaxies to the first quasars. Now, I want to be fair about the caveats, because your listener should know the soft spots when they try to reproduce it.
Please, let's do the honest accounting.
First caveat, box size. Their main runs are in a 2 megaparsec box, which is small. A small box distorts the halo mass function and undersamples massive halos. They patch this by tracing halos in a 20 megaparsec box and doing a 40 megaparsec box for high redshift, but the statistics on the biggest halos are thin. That's the larger scatter they mention. Your listener will feel this. Small boxes are cheap, but bias the massive end. This is, I believe, exactly the tension the project ran into, needing a bigger box to constrain the massive halo end of the slope.
Second caveat, resolution, and the A is constant assumption.
The scaling symmetry we leaned on so heavily requires it to be approximately constant while the core forms. That's justified because cores form fast compared to the Hubble time, but it's an approximation, and near major mergers or rapid accretion it could wobble. And resolution, they need the core resolved by many cells. They do the 8 times convergence test on one halo, which is reassuring, but it's one halo. A full convergence study across the mass range would be the gold standard, and that's expensive. Your listener doing systematic convergence testing is genuinely pushing beyond what the original paper could afford.
Third, the alpha equals one choice.
They set the dimensionless constant alpha to 1 to draw the analytical line. It's measured to be close to 1 from the merger experiments, but close to 1 is doing some work in the normalization. If alpha were, say, 1.3, the normalization shifts, and so would the inferred boson mass. So for precision work, alpha is something to measure carefully, not assume. It's a modest but real source of systematic uncertainty in going from the slope to a boson mass.
And fourth, no baryons.
No baryons, no gas, no stars, no feedback. This is pure dark matter. The high redshift quasar story is a conjecture precisely because it invokes gas that isn't in the simulation. Adding baryons could change core structure through gravitational back reaction. They flag that larger simulations with baryons are needed, and that's still frontier work today. So the core halo relation itself is robust dark matter physics, but the astrophysical payoffs need baryons to be believed fully.
Let me step back and ask the meta question. Why is the scaling symmetry the thing that makes all this possible? If Schrödinger-Poisson didn't have that symmetry, would any of this hold?
Beautiful question. The symmetry is what makes the soliton a one-parameter family rather than a single rigid object, and it's what lets a soliton continuously adjust its size to match whatever halo it finds itself in. Without the scaling symmetry, you couldn't have self-similar cores of every size, and the core wouldn't be able to tune itself to the halo velocity dispersion. The symmetry is the reason the core-halo relation is a smooth power law rather than a single fixed core mass. So yes, in a very real sense, the one-third exponent is a shadow of the scaling symmetry of the Schrödinger-Poisson equation.
And the symmetry comes from the fact that Schrödinger-Poisson has no intrinsic length or mass scale once you're in the high-density regime.
Exactly, it's scale-free in that regime. There's no built-in length. Gravity, the Poisson equation, is scale-free, and the free Schrödinger equation is scale-free, and when you couple them, the combined system inherits a scaling symmetry. The only thing that breaks the scale freedom and picks a physical size is the boson mass, which enters through the units, and the boundary conditions, which is the halo. That's the deep reason the boson mass sets all the physical scales, and the halo sets which member of the family you get.
Let me test my understanding with a quick thought experiment. Suppose I double the boson mass. What happens to a core in a given halo?
Let's read it off the equations. The physical core radius r sub c goes as m22 to the minus 1, so doubling the mass halves the core radius. The core density goes as m psi to the minus 2 from equation 3. But wait, be careful, that's at fixed core radius in kiloparsecs. Let's just trust r sub c, proportional to m to the minus 1 and core mass. The minimum mass scale m sub m0 goes as m to the minus 3 halves, so it drops by a factor of 2 to the 3 halves, about 2.8. So a heavier boson gives smaller cores and a lower minimum galaxy mass. Push the mass high enough, and fuzzy dark matter becomes observationally indistinguishable from cold dark matter. The cores shrink below detectability. That's precisely how upper limits on the boson mass are set.
And that's the tension in the field. Dwarf galaxy cores want a lightish boson, around 10 to the minus 22, but Lyman alpha forest data want a heavier one.
That's the live tension. The Lyman alpha forest measures small-scale structure in the intergalactic medium, and it prefers a boson heavier than 10 to the minus 22 electron volts, which would make cores too small to solve the dwarf problems. This paper is on the optimistic side, arguing the PSIDM power spectrum has a sharper break than warm dark matter and is marginally consistent, and that adding about 10% cold dark matter relieves the tension. But it's genuinely unsettled, and it's why nailing the core-halo relation observationally and in simulations like your listeners matters so much. Every independent handle on MPSI helps adjudicate.
Let's consolidate the key equations one more time as a spoken cheat sheet, because I think that's the most useful thing we can leave people with.
Let's do the cheat sheet. Number 1, the scaling symmetry. Under lambda, time goes as lambda to the minus 2, length as lambda to the minus 1, psi as lambda squared, potential as lambda squared. Number 2, the physical quantities. Core radius as lambda to the minus 1, density as lambda to the 4th, mass as lambda to the 1, energy as lambda cubed. Number 3, the immediate consequence. Core radius times core mass equals a constant, so core radius is inversely proportional to core mass.
Keep going.
Number 4, the soliton profile. Density equals 1.9, a to the minus 1. Boson mass in units of 10 to the minus 23 to the minus 2. Core radius in kiloparsecs to the minus 4. All over the bracket 1 plus 0.091 times radius over core radius squared to the 8th power. Number 5, the energy relation from the mergers. Core mass equals alpha times the square root of specific energy, the modulus of E over m. Number 6, its meaning, core mass proportional to halo velocity dispersion, equivalently core radius times velocity dispersion of order 1, the non-local uncertainty principle.
And the headline.
Number 7, the headline core-halo relation. Core mass proportional to a to the minus 1/2 times halo mass to the 1/3. Number 8, the physical core radius, proportional to boson mass to the minus 1 times halo mass to the minus 1/3, about 1.6 kiloparsecs for a 10 to the 9th solar mass halo at redshift 0, with m22 equals 1. And number 9, the minimum halo mass, about 4.4 times 10 to the 7th over m22 to the 3 halves solar masses. That's the paper in 9 lines.
If our listener remembers only one derivation, which one?
The 1/3, energy goes as mass cubed, so mass goes as root-specific energy. Specific energy is velocity dispersion squared. Velocity dispersion from virial equilibrium is root of halo mass over virial radius. Virial radius is halo mass to the 1/3. Chain it, root of halo mass over halo mass to the 1/3 equals halo mass to the 1/3. If they can rederive that standing at a whiteboard with no notes, they understand the paper.
Let me push on one thing that always trips me up. The two scalings, lambda and the A rescaling, give me the one-sentence distinction one more time, cleanly.
The lambda scaling is at fixed cosmic time and relates different solitons of different sizes to each other. It's the internal symmetry of the equation. The A rescaling is over cosmic time and describes how a single soliton's comoving description drifts as the universe expands, giving the comoving core radius shrinking as a to the minus 1/4 and the extra A factors in equations 4, 6, and 7. Internal symmetry versus cosmological evolution. Two different jobs.
And practically, for someone fitting simulation output, which redshift factors do they need to be careful about?
The a to the minus 1/2 in the core halo relation and the a to the 1/2 in the core radius are the big ones. Their order unity effects across the redshift range they simulate, z from 12 to 0. The zeta of z over zeta of 0 factors to the 1/6 or minus 1/6 are slowly varying, small corrections, since zeta only moves from about 180 to 350. So if you're comparing halos at very different redshifts on one plot, apply the A factors carefully. That's what makes the different redshift points in Figure 2 coalesce onto a single line. Miss them and your relation looks like it has scatter that's really just redshift evolution.
That's a concrete gotcha. Any others you'd warn them about?
Two more. First, the factor of 4 between core mass and total soliton mass. Core mass is mass within the half-density radius, only about 25% of the soliton. If you accidentally compare their core mass to your total soliton mass, you'll be off by 4 and think the normalization is wrong. Definitions matter. Second, the units. The whole paper is in normalized code units where h bar over m equals 1, and the conversions to solar masses and kiloparsecs carry the boson mass. Get the unit conversion wrong and you'll misinfer the boson mass while the dimensionless slope still looks fine. The slope is unit-proof, the normalization is not.
That distinction, slope is unit-proof. Normalization carries the physics, might be the single most useful sentence for someone reproducing this.
Think it is. It tells you what to trust as a code check versus what to treat as a measurement. Get the 1/3 slope, congratulations. Your Schrödinger-Poisson solver respects the scaling symmetry and virial equilibrium. Now the real work begins. Get the normalization right and you can say something about the mass of the dark matter particle. One is verification, the other is discovery.
Let's zoom out to close. Why does this paper still matter more than a decade on?
Because it's the reference point. Any fuzzy dark matter simulation, any theoretical model of a soliton in a halo, gets compared to Schive 2014's core halo relation. It defined the observable. It turned a vague idea, quantum pressure makes cause, into a quantitative, falsifiable law with an exponent you can measure. And it did it by marrying a symmetry argument to a heroic simulation, which is exactly the combination your listener is reaching for. A differentiable solver to get the symmetry and the gradients, and adaptive mesh runs to get the resolution. This paper is both their target and their template.
And the intellectual beauty, for me, is that the uncertainty principle, which you meet as a statement about a single electron in a box, turns out to govern the architecture of an entire galaxy, non-locally, tying the core in the center to the motion of the whole halo.
That's the poetry of it. A galaxy-sized manifestation of a rule from your first quantum mechanics lecture. The core radius times the halo velocity dispersion is of order 1, position times momentum of order h bar, written across 100,000 light-years. The scaling symmetry lets the soliton pick its size, the granules carry the message from halo to core, and virial gravity closes the loop into 1/3. Nature rarely hands you an exponent that clean with a derivation that honest.
George, that was exactly the deep dive I wanted. To our listener building the fuzzy dark matter simulation, your 1/3 slope is the handshake that says your solver is honest and your normalization is where the boson mass is hiding. Go measure both.
Reproduce the slope to trust your code, measure the normalization to constrain the physics, and never confuse core mass with total soliton mass. That's the paper, spoken out loud. Thanks, Alice.
Thank you, George, and thanks everyone for studying Schive et al. 2014, the core halo relation of quantum wave dark matter with us.